name is Dimitrios Papastergiou. I'm working for the Swiss Federal Roads Office and I'm head of bridges. My tasks concern the revision and elaboration of standards for the Swiss highway bridges. I'm glad to participate today in this international seminar where I will present you some rehabilitation examples concerning the use of ultra high performance fiber reinforced concrete in bridges. Thank you. Here's the content of my presentation. I will start with a short description of the Federal Roads Network and bridge assets. Subsequently, I will present briefly some characteristics of the ultra-high performance fiber reinforced concrete as a building material and make a mention of the related Swiss standards. Thereafter, I will present some case studies concerning interventions in which this material was used for the rehabilitation purposes. Finally, before arriving at the conclusion, I will present some perspectives of the use of this material for new structures. In the illustrated map, you may see in green color the existing national road network, and in violet, the 400 kilometers of cantonal roads which were joined to the national network in 2020. The total national road network is thus actually 2,254.5 kilometers. In blue, the remaining parts to be constructed, which is about 33 kilometers. It is a quite complex network due to the particular topography of Switzerland and comprises 4,330 bridges, including flyovers and underpasses, as well as 320 tunnels. Now, most of the Swiss bridges are constructed in the period from the mid-60s to the late 70s, so their average service life is around 50 years. Degradation process, increase of traffic load, especially heavy traffic load, as well as evolution of codes makes it necessary to proceed regularly to important rehabilitation projects for several of these bridges. With an annual investment of around 1% of the replacement value, the bridges are kept in a good or acceptable condition. Concrete is the predominant building material in Switzerland for our road bridges. 83.5% of the total area of the bridge decks is associated to reinforced concrete or prestressed concrete bridges. However, despite the advantages that have led to the use of the concrete as the main building material, the issue of durability was not thoroughly examined or taken into consideration in the past. A combination of factors such as exposure to corrosion, defective conceptual details, particularly to the abutments, presence of alkali aggregate reaction, carbonization, frost, use of de-icing solutions in winter period, and other have resulted in some cases to important damage, which normally should not occur during the design service life of a bridge. For this reason, other material, more efficient and more resistant to environmental influence, have been sold since the 90s. Such a promising material is the ultra-high performance fiber reinforced concrete. Now, this material is neither a concrete nor steel, but an advanced composite cementitious material with specifically tailored properties. That's the reason why several experts call it ultra-high performance fiber reinforced cementitious instead of ultra-high performance fiber reinforced concrete. I rather agree, however, in this presentation I will use the initial nomination in English. Now, the cement content is more than 2 times higher than for a normal concrete. For instance, for an ordinary concrete, the cement content is between 250 to 400 kilograms per cubic meter, whereas for the ultra-high performance fiber reinforced concrete, the cement content is 700 to 1,000 kilograms per cubic meter. It contains silica film, which fulfills 3 functions. It fills voids between cement grains, it enhances their rheological characteristics, and informs hydration products by pozzolanic activity. Thus, the mechanical strengths are increased and microstructure and compacity of this material are enhanced. The water-to-cement ratio in ultra-high performance fiber reinforced concrete is less than that of a normal concrete. In an ordinary concrete, the water-to-cement ratio is between 0.35 to 0.65, whereas in ultra-high performance fiber reinforced concrete, the water-to-cement ratio is less than 0.25. So, due to the low water content, superplasticizers are essential for the workability, and they are in much higher content than that for a normal concrete. A significant difference of the composition of this material in comparison to the normal concrete is the absence of aggregate. Other quartz sands is used with particle less than 1 quartz sand is used with particle size less than 1 millimeter in this material, whereas in ordinary concrete we have aggregates which can reach the 32 millimeters. This is why we should not call it a concrete but a cementitious material. Ultra-high performance refers principally to improved mechanical strengths, structural toughness, and durability. The typical behavior of ultra-high performance fiber-reinforced concrete in a uniaxial state of stress in comparison to other concretes is shown schematically in this slide. The diagram on the left shows the typical response in uniaxial tension. In the left diagram, OC are the initials for the ordinary concrete. FRC are the initials for the ordinary concrete with fibers. HFRC are the initials for the high-strength concrete with fibers, where ECC stands for engineered cementitious composites. As we can see, ordinary concrete has an upward failure in tension, whereas the concrete with fibers, they have a strain branch, but they don't present any strain hardening. The engineered cementitious composites and the ultra-high performance fiber-reinforced concrete are distinguished between other concrete with fibers as materials exhibiting strain hardening in tension. Moreover, for ultra-high performance fiber-reinforced concrete, the resistance in uniaxial tension is more than double in comparison with that of other concretes with fibers. The diagram on the right depicts the response in uniaxial compression. Ultra-high performance fiber-reinforced concrete is a material with a cement matrix of a characteristic compressive strength in excess of 150 megapascal, which is more than double of that of a high-strength concrete. Now, let's see more in detail the structural response in tension of ultra-high performance fiber-reinforced concrete and how it is different from that of ordinary concrete with fibers. For ultra-high performance fiber-reinforced concrete, in the first part of the curves until point A, the stress rise is quasi-linear and elastic until the cracking strength. After cracking, a strike hardening takes place until point B, with post-cracking strength being higher than that of the cracking strength. Up to point B, multiple cracks are formed during the strain hardening. However, the macroscopic deformation is still uniform and can be expressed by the strain epsilon. This is of high importance for the sealing properties of the ultra-high performance fiber-reinforced concrete, as we will see later on. At point B, a crack localization occurs and softening behavior is observed. Now, ordinary concrete with fibers do not present strain hardening. A main crack is formed, followed by fibers. They are characterized by the material, by its mechanical properties and their geometry. In order to enable the transfer of force with a small crack opening and to sustain tensile forces without breaking, a high modulus of elasticity and high strength are required. The modulus of elasticity of steel fibers is 200 gigapascal, and strengths are in the range of 1,000 to 3,000 megapascals, with a deformation at failure at about 3 to 4%. Fiber content is usually expressed in terms of fiber volume fraction, representing the ratio between the fiber volume and the material volume, the latter being the matrix with the fibers. Fibers quantity varies in different types of this material, usually in the range of 1.5 to 2.5%, and in certain cases, for specific applications, it can reach up to 6%. For applications using ultra-high performance fiber-reinforced concrete, we use in Switzerland the recommendations of the Swiss rule SCA 2052 from 2016. This document has not the status of a code yet, so it has not an obligatory character. It handles several issues, such as the material properties and the constitutive laws. It also provides guidelines for design, such as shear, bending moment, and other. This manual, which is currently under revision, provides also constructional features and disposition, such as the sealing of the working joints. It defines the tests which are required to verify the material properties. A very useful information is the criterion for the sealing properties of the ultra-high performance fiber-reinforced concrete. Based on experimental investigation, it was found that as long as the tension strain in this material remains in serviceability limit state lower than 0.1%, 1 to 1,000, the sealing properties are maintained. This is of extreme importance since it allows, when designed so, to avoid using complementary layers of traditional sealing for the decks of the bridges and thus avoiding unnecessary costs and delays during an intervention. Since 2003, Swiss counts more than 270 recorded applications with this material. This corresponds to a total volume of more than 9,490 cubic meters. It's worth mentioning that more than 80% of these applications concern rehabilitation or retrofitting projects of road bridges, federal and cantonal. In the following slides, I will present few of those case studies. Now, Sillon viaducts are two parallel highway reinforced concrete bridges, each carrying one direction, opened to traffic in 1969 and located in the shores of the Lake of Geneva near Montreux in Switzerland. They consist of variable height box girders by post-tensioning segmental construction with epoxy glued joints and spanning between 92 and 104 meters at a total length of 2,120 meters. In 2012, during rehabilitation works on the viaducts, early signs of the alkali aggregate reaction were discovered in the concrete. In later stages, this reaction could lead to deterioration of the concrete compressive strength, which would mean an insufficient structural safety for the resistance of the bridge at ultimate limit stage and even worse at serviceability limit stage. It was thus necessary to develop a concept for rehabilitation and strengthening to protect the concrete from water ingress, slow down the rate of alkali aggregate reaction, and increase the ultimate resistance and stiffness of the deck slab and girder in view of potentially reduced strength and modulus of elasticity of the existing concrete. Such an intervention had to be cost-effective in terms of direct construction costs and in terms of also of user costs. It had also to preserve the form and hence respect the cultural value of the bridges. The chosen strengthening concept was adding a layer of ultra-high performance fiber reinforced concrete, additionally reinforced with steel rebars in the two directions, longitudinal transversals, also serving as a waterproofing layer. The new 45 millimeter thick layer on the bridge deck provides an effective and significant improvement of the structural performance of these viaducts. By casting one layer of ultra-high performance fiber reinforced concrete on the deck slab with rebars in the transverse direction and in the longitudinal direction, the following beneficial effects were achieved. Increase of the deck slab's ultimate resistance in the transverse direction in bending and in shear. Increase of the deck slab's stiffness to enhance the serviceability of the slab and the fatigue safety of the existing reinforced concrete elements in view of future high traffic demands in number of vehicles and axle loads. Increase of the hogging bending moment resistance and the stiffness in the longitudinal direction of the box girder. Provide waterproofing to protect the existing concrete of the slab from water ingress and thus limiting the further development of the alkali aggregate reaction. Limit duration and cost of the derivation by realizing all the above listed requirements and structural factors by casting of just one layer of ultra-high performance fiber reinforced concrete. For this purpose, a machine was developed specifically for the casting application of this material, and the quantity of it was 1,125 cubic meters for each of the 2,000 kilometer of the 2 kilometer viaducts. The casting took place in July 2014 for one of the bridge and in June 2015 for the other bridge. And the intervention cost was 200 euros per square meter of deck surface, 50% of it being the cost of the material itself. Now, let's see more in detail the obtained increase of the bending and the shear resistance of the slab in the transverse direction. The Conking Bridge deck slab has a total thickness of 180 millimeters. The transversal 60 millimeter diameter top steel rebars are placed at the height of 152 millimeters from the intrados, and they are spaced at 12.5 centimeters. The center of these rebars is at 60 millimeters only from the top of the concrete. There is experimental evidence that in pure bending, no debonding occurs between the concrete section and the new layer, when the concrete substrate has been prepared properly by high-pressure water jet and the substrate has been wetted before the casting. The composite section thus behaves monolithically up to maximum resistance. Based on this observation, the transversal bending resistance of the deck slab is calculated using plane strain analysis. The upper left figure shows the developed forces with ultra-high performance fiber reinforced concrete in tension due to negative bending moment. Rectangle here. Considering now a future reduced strength due to the alkali aggregate reaction of the concrete limited to 20 megapascal, the maximum resistance for the sections 1 prime here on the cantilever is equal to 165 kilonewton meter per meter. This is 73% higher than the resistance of the reinforced concrete itself in the stage before the reinforcement. For positive bending moment, the layer of the ultra-high performance fiber reinforced concrete is in compression and mainly contributes to the resistance by reducing the height of the compression zone and thus increasing the static height. For the case of the considered here, the positive bending resistance at the section here in the middle of the slab is increased by 33%. Now, the deck slab of the Sion viaduct does not have any shear reinforcement. Shear resistance of the concrete element is thus calculated as a combination of the concrete contribution and the contribution of the ultra-high performance fiber reinforced concrete. The contribution of the concrete depends on the concrete carries the inclined compressive stress ahead of the crack tip and fails by crashing at the compression zone. So the contribution of the concrete depends on its compressive strength and the angle of the inclined shear crack. The widening of the inclined crack in the concrete section creates a prime action of the ultra-high performance fiber reinforced concrete layer, which resists by bending out on plane in double curvature. Here, this is accompanied by a softening of the concrete in the concrete volume under the layer, called intermediate crack-induced debonding zone. Now, the contribution of the ultra-high performance fiber reinforced concrete to the shear resistance is thus a function of its bending resistance in double curvature over the length of this zone. The length of this zone is estimated from the mouth of the inclined crack to the position of the concentrated load. It thus depends on the angle of the inclined shear crack and on the length of the shear span. For the present slabs, the shear span corresponds to the distance between the side of the concentrated willow and the web of the box girder. It is equal to twice the effective flexural depth of the composite section, as shown here for the cantilever slab. With an angle of the inclined crack estimated at 35 degrees, the shear resistance of the composite section is 265 kilonewton per meter. The contribution of this in this resistance of the ultra high performance fiber reinforced concrete is about 1/3 of the total resistance. The study has shown that in this particular slab, the flexural failure mode is much more likely to occur also in the case of shear-prone loading situation. Now, the aforementioned project of the rehabilitation of the Sion viaduct by means of ultra-high performance fiber reinforced concrete received an excellence award from the American Concrete Institute. Another common application is the rehabilitation and strengthening of corrosion damage zones, such as curbs, webs, and crash barrier walls. It is the case of the bridges Cadrex, Poly, Metlen, Linden, and N1-519 in Kilvangen. The advantages for a price similar to conventional mortars are the following: excellent adhesion to the substrate, self-stressing condition, and waterproof and increased resistance to chloride penetration. Technological development allows nowadays to cast very thin layers of ultra-high performance fiber reinforced concrete for this purpose. More specific, at the case of the bridge in Kilvangen, and the figure here on the right, the rheological properties were improved for easy pouring into a 3 centimeter only wide formwork to fill a height of 100 centimeters, including a non-resultant part at the top of the crash barrier wall and at the bottom of it in the continuity with the bridge deck waterproofing. Another interesting application is the widening and the supporting of the existing decks by means of inclined struts made of ultra-high performance fiber reinforced concrete. It is the case of the Podez viaducts. The bridges over the Podez River, located in the cities of Puyi and Belmont, allow motorway 9 to cross the valley formed by the river with the same name. The two structures, to traffic in 1974, were built using the balanced cantilever method. Each bridge has 5 spans, as you can see here in the figure, with the longest span being 104 meters. The latest inspections have revealed several damages. More precisely, concerning the slab, the cantilevers were found to be in poor condition, with spalled concrete and corroded steel reinforcement on all edges. Furthermore, future requirements for diverting the traffic during important rehabilitation work on the highway necessitating widening of the deck. Any possible intervention had also taken into account the replacement of the curbs by concrete crash barrier walls for enhanced security against lateral shock. The solution proposed was to widen the deck slab by ordinary reinforced concrete and supporting its widened cantilevers with struts, allowing to maintain the existing steel reinforcement in the slab and thus minimizing the intervention on the deck. The struts were made of ultra-high performance fiber reinforced concrete to minimize their weight and to avoid their future maintenance, which would be the case if they were made of steel. In total, 816 such inclined struts of 5 types were produced. The ultra-high performance fiber reinforced concrete struts were prefabricated, allowing thus to reduce their cost at 500 Swiss francs per unit, whereas the joints with the web of the longitudinal girders and the cantilever slabs were assured by cast inside of ultra-high performance fiber reinforced concrete. Prior to construction, several configurations of the prefabricated struts were tested in the laboratory. This allowed to verify the allowed eccentricity during execution and mounting of the struts, which is found to be 1 centimeter. After realization, it was apparent that the inclined struts of ultra-high performance fiber reinforced concrete maintained consistency with the existing concrete and the geometrical form of the existing structure, preserving thus the cultural value of it. Now, the previous example show how ultra-high performance fiber reinforced concrete can be used as building material for structural members destined to rehabilitation interventions. Other such members are the crash barriers or curbs on the edge of the cantilever slabs. This can be the case when, for instance, the existing curbs are highly deteriorated and need to be rebuilt partially or even totally. Applying a life cost analysis, it can be proven that the use of ultra-high performance fiber reinforced concrete instead of ordinary concrete is more economic and technically efficient. This is the case of the reconstruction of the curb and the part of the slab of the bridge de Raffinerie in the Highway 9 shown in this slide. The project is under call for tenders for works. Now, in the cases when retrofitting and rehabilitation costs are high, and the retrofitting results somehow questionable due to the missing precision of the quality and the state of the existing remaining materials, a replacement of a bridge by a new structure can be an alternative solution. It is the case actually of several overpasses on the Highway 1 between the cities of Lausanne and Geneva. These overpasses, they were built in the early 60s. They present 3 spans. The main span supported by inclined struts. They are made of pre-stressed and reinforced concrete and are a type of integral bridges. The inclined struts and the deck are linked together, but also to the inclined abutments. Despite their very efficient static system, because it diminishes the span, these bridges are in a very deteriorated state due to defective sealing. Furthermore, they were not designed to stand the heavy traffic of today. Rehabilitation and retrofitting becomes extremely expensive in such a way that reconstruction seems to be a more efficient solution. In such a case, it's worth evaluating through a life cycle analysis whether the use of prefabricated bridges made of ultra-high performance fiber reinforced concrete can be the optimal solution. The slide shows here the concept of such a new overpass over the highway in the community of Bursan. The overpass consists of ultra-high performance fiber reinforced concrete girders with pre-stressing and abutments made of ordinary reinforced concrete. The new bridge is integral with one clear span of about 42 meters. The project is still under development phase and should conclude to optimization of the ultra high performance fiber reinforced concrete pre-stressed girders, since the preliminary design is by its nature somehow conservative and does not allow to take advantage of the enhanced mechanical properties of this material. For instance, the actual design contains stirrups, shear reinforcement, which can be avoided. Overpasses built elsewhere in the world, like in France, present ultra-high performance fiber reinforced concrete girders, which carry the shear force by the contribution of the shear resistance of this material and by the contribution of the post-tensioning. The detailed project of the aforementioned case study is expected to be delivered during 2022. After all the above information, we may arrive to the following conclusions. Ultra-high performance fiber reinforced concrete is a building material with enhanced mechanical characteristics in comparison to ordinary concrete or to ordinary fiber concrete. Due to its sealing properties and high resistance against corrosive agents, it is suitable for rehabilitation intervention for bridges. Standardization and prefabrication may help to reduce its high production costs. Ultra-high performance fiber reinforced concrete can be used both as building material for reparation and reconstruction locally of hybrid members, as well as a substitute to ordinary concrete for building new elements or even new structures combined with pre-stressing or steel construction. Despite its high production costs, it should be examined as an alternative to ordinary concrete under, of course, a life cycle analysis. On the last slide, I have included here the most important references which were consulted for this presentation. I would like in this point to thank you for your attention, and I will be glad to answer to any questions. Thank you again.